Hi, I'm James Mahoney. This video is designed to supplement an in-person class. Real-time rendering is a little complicated and it's tricky, but it's also really rewarding. So let's dive in. Before we get too deep into specific Unity settings, it's very helpful to have at least a general understanding of computer graphics. You should have a rough idea how the rendering algorithm works and the core concepts of lighting and materials. Then we can focus on what you need to do to get your work rendering beautifully. Good rendering is essential for portfolio work. History of rendering algorithms is a good way to begin to understand it. Ray tracing was really huge in the late 70s and early 80s. It was an amazing invention, really. This is the core concept, is that it's easy to generate a vector and trace it as it bounces around the environment. Basic math with some trigonometry and linear algebra. And it works a little bit like this. You shoot the ray into the scene by sampling the screen or image plane. Clearly, more samples will generate a better image, right? Then you calculate what object gets hit, and then determine the color at that point, taking into consideration the material and the lighting. Determining if something is in shadow or not is always very tricky, especially given the limited computing power of those early days. Once an object is hit, you have to then make a ray to each light in the scene and check each object in the scene and see if that ray is blocked by anything. That's crazy, right? The shadow calculation and sampling errors were the biggest challenges of the day. Once it's determined what object was hit and exactly where, then some interesting calculations need to be performed. The resulting pixel color is based on the accumulation of light affecting that point on the surface. It's all the propagation of light in an environment. This process is recursive as rays continue to propagate until a limit is reached or the contribution falls below a threshold. The resulting color of an intersected point on a surface is based on the bidirectional reflectance distribution function, otherwise known as the BRDF. Light hits a surface and then bounces off depending on the nature of that material. Specular reflection bounces off in the mirror direction, but light can bounce in all directions based on the roughness of the surface. Rays are recursively bounced and transmitted through transparent materials and propagate through the scene. Here's a common diagram of the BRDF. This function determines the pixel value of the surface from any viewing angle given the surface normal and the light angle. This function, the light distribution, is a function of the material properties. But remember, it's really a three-dimensional shape. Ray tracing is essentially a sampling problem. Most artifacts are from insufficient samples. Ray tracing over the years got a lot more sophisticated to increase speed and ability to render different types of things. Here you can see the results of being a bit smarter about which rays to shoot into the environment, otherwise known as importance sampling. The algorithms work really well for specular surfaces, shiny things, but somehow they didn't quite look photoreal. Something was missing. Can anyone see what's interesting about this computer-generated image? Right, it's the diffuse reflections as the ambient light bounces around the environment. Notice the red glow on this box and the green glow on this other box. This is usually called diffuse lighting or indirect lighting. To capture this, you have to evaluate the relationship of every surface to every other surface in the scene. So this is even more computationally expensive than ray tracing. I was at Cornell working in the computer graphics lab in the 1980s when this algorithm was developed. So this is the famous Don Greenberg and Michael Cohen Cornell box experiment, and it marks the invention of global illumination, which was then called radiosity, to capture indirect lighting. An actual physical box was built, and algorithms were developed and compared in a controlled experiment until people could not tell which was the real box and which was the computer rendering. That was in about 1983. Direct illumination is a simple ray-traced image based on surfaces and their orientation to light sources. The example on the left includes an ambient component as well, or else it would be no light on the walls and ceiling. And that ambient bit was just sort of a hack. Radiosity, or sometimes called indirect illumination or global illumination, improves images in multiple ways. Can you see two things that are better in that image on the right? One is the color bleeding, the red, and then it also has more accurate cast shadows. Direct illumination on the left, without the ambient component hacked in, and the global illumination render on the right, direct and indirect lighting. Understanding direct and indirect lighting is critical for getting good real-time rendering in Unity. Beyond direct and indirect illumination, there's ambient occlusion. It's also sort of a hack to make images better. Ambient light in the environment can't get down into the little tiny nooks and crannies of a geometry. This is irrespective of lights and material. It only considers the geometry and the proximity of faces. It's white where there's nothing nearby, and no facing polygons, and it's dark where there is something that's close, and it makes the nooks and crannies extra dark. We usually would put this on a multiply layer. It would be multiplying into the color that's in the scene. This rendering kind of has examples of many rendering features. You can see if you can pick out some of these. There's direct illumination, diffuse reflection, specular reflection, refraction, subsurface scattering, such as like what you have with skin, ambient occlusion, caustics, depth of field. And this image goes even further. Ray tracing, global illumination, plus caustics, refracted light, and participating mediums, volumetric fog. Someday we'll have all of this running in real time in VR. There's other kinds of things that you can do with materials. There's sheen and clear coat and anisotropic reflections. And so the complexity of rendering algorithms means lots of settings and switches to get certain looks. And this is very complex in Unity. Let's review the core algorithm and consider some of the issues you need to deal with in real-time rendering. A ray is calculated from the eye and shot into the scene and recursively bounces around until it reaches a limit where the color of the given pixel is determined. Remember that for each intersection, a light calculation needs to be determined. Am I in shadow from that particular light? Light calculations are very expensive. It's easy to calculate the ray per pixel. Various methods are used for shooting multiple samples with random jittered angles, because samples are very, very important. And you've seen this in Maya rendering, how sampling is so important, but it's really important in real-time rendering as well. Sampling errors are tricky. They can cause rendering artifacts, usually called aliasing. Path tracing, bidirectional path tracing, and MLT, Metropolis Light Transport Algorithm, using Monte Carlo sampling. This is the samples number used in renderers such as Arnold. So this is the gold standard, and someday all real-time renderers will probably use something like this. This shows path tracing sampling values. With path tracing, you can have it all: soft shadows, light bleeding, ambient occlusion, and more. But in reality, currently today, real-time renderers use a lot of cheats or tricks to get the job done. Let's touch on this just a bit. While the High Definition Render Pipeline, or HDRP, uses real-time ray tracing, there are faster rendering paths used by the Universal Render Pipeline, or URP. Forward rendering is the default path. These paths use image buffers to store calculations such as normals, depth, specular, colors, etc. And then they calculate from there the final colors very, very fast. To speed things up for dynamic real-time lighting, some lights can be set to shade per vertex instead of per pixel. This doesn't really look so good. So designers usually have main lights that are per pixel, but additional lights can be per vertex to speed things up. One shortcut that's used for determining cast shadows is to render light as if it were an image from the viewpoint of the light source projected out into the scene. If you sort of invert that, you have what's called a shadow map, which is essentially an image that will indicate the cast shadows as they project onto objects. This opens up the sampling problem of having enough pixels for shadow maps. We'll look at how to get this set up correctly. But the real trick is to recognize that much of the lighting information can be pre-computed and painted onto the surfaces. This is called light map baking, and it is the essential key to creating gorgeous scenes in VR. All your objects can be unfolded to create light maps. Nothing can overlap in the maps though. And note that only things that are not moving or are view dependent, like specular highlights, reflections, and refractions, can be baked into light maps. Light map baking is the essential key for this work in this day and age. Light probes are kind of an interesting way to handle dynamic objects. Dynamic objects can't have baked light maps for hopefully obvious reasons. And light probes pre-calculate the lighting at a point in space. Then, as objects move around, the nearest probes are used to interpolate an approximation of the actual lighting on the dynamic objects. That's pretty cool, huh? And they're pretty easy to set up. Similarly, reflection probes are used to pre-calculate what the world looks like from a particular point in space. It's a cube map, essentially. And then at runtime, the reflected vector that's discovered from off a surface is used as a basic lookup or an index into the nearest reflection probe. This is also a very cool trick. Okay, quick review. Direct lighting is for the initial illumination of objects with lights, while indirect is how light bounces around off all surfaces in a scene, and this is called global illumination. The challenge is to best capture this phenomena with real-time rendering. Unity offers some options. Real-time rendering for all lighting and materials for each frame would be ideal, but it's too expensive today in most cases. Baked rendering is good for static objects and low-powered devices, but cannot capture lighting and shadows of things that are moving, as well as view-dependent phenomena, such as reflections and specular highlights. Mixed will bake indirect lighting and allow real-time rendering for direct lighting and view-dependent phenomena using reflection probes. As I've said before, baked light maps are key for real-time rendering, but there's some choices to make, in particular with cast shadows. Shadow masks are fast, but they don't look very good. Baked indirect will use real-time lighting for cast shadows and bake all the indirect lighting, and this is probably the best option. Subtractive is sort of a cheat. It's faster than baked indirect, and in this case you specify a shadow color, which will then be subtracted at runtime to create a dynamic cast shadow. One color for this is often not quite right and can look bad in some situations, but it is a bit faster. There are also some choices to be made when setting up shadow maps, if they're used, for real-time dynamic cast shadows. Let's look at some object materials. Material properties can be modulated across a mesh face by using the UV mapping to index into a 2D image that can then change the material's property at that particular location on the mesh. UV mapping is also important for baking light maps. Material maps that do this are albedo, which is the actual color of something, the normal map, which adjusts the normal of the surface to suggest more texture and complexity than there really is in the geometry. Specular and metallic maps can be used to indicate which parts are shiny and which parts are dull. AO, or ambient occlusion, is used to create a little extra dark in the deep recesses of a shape. Of those, normal mapping might be the strangest to understand. Here, the geometry is not changing along the face of this cube, but the normal map is telling the renderer to change the surface normal at a specific point based on where it is on the 2D normal map. That's a really good trick, right? If you find this stuff interesting, I strongly suggest you take some computer graphics classes here at Dartmouth. Professor Wojtek Yarrow, for instance, is a world-renowned expert, and he's a great teacher, and we have lots of great opportunities for people to learn a lot more about this computer graphics stuff. It's not easy to get a real-time engine to render beautifully, but ultimately, as can be demonstrated, with some effort, amazing results can be achieved. There are a ton of settings in Unity that affect rendering, and unfortunately these settings are kind of spread out, including project settings, scene settings, lighting settings, material properties, texture properties, and light properties. And so the combinatorics of all these things it's mind-numbing. Okay, let's look at some specific things in Unity. You can find the rendering settings by verifying it, which is in the project settings under graphics. Clicking on this will find it in your project panel. Open it, and you'll be able to see the values that are in the inspector. Switching between the low, medium, and high qualities and watching how the settings change can be really instructive. You might want to turn on high dynamic range, set anti-aliasing to 4x, have your main light at least be per pixel, and up the shadow resolution, if possible or needed. 2048 should work in most cases. Mainly though, you will want to look at your scene and adjust the max distance for your shadows. You don't want them blinking off while in the game, but you want to get the maximum resolution for areas near the player that are important. You can adjust these settings to avoid the jagged cast shadows. Depth and normal bias might need to be brought down to avoid some weird shadow leaking around corners and the creation of these odd patterns that are objects that are starting to self-shadow. And we can go over this more in class. You can adjust bias on a light-by-light basis, but it's best to do it here globally for the entire scene. The next important panel to check out is the lighting panel. Select the tab Scene up top. At the top, you want to create a new light setting asset. You put this in your settings folder and give it a unique name. I recommend these following settings: Baked Global Illumination, Lighting Mode Baked Indirect, and the box below that will remind you what these different options mean. And for light map settings, use Progressive GPU if you can, depends on your hardware. Light map resolution will greatly influence the quality and speed of baking. On a PC, try 20 or so until your final bake, which might be as high as 40 texels per unit. On a Mac, somewhere between 5 and 10 will do for working, and then you up that later when you do your final bake. Max light map size probably should be about 2048. The higher the quality. Light map compression. Try none or high quality unless you're having problems. This will increase the memory required to run. Turn on ambient occlusion and tune the max distance and contributions until you have a significant but still subtle effect. And this is trial and error, depends on the scene. Try these values to start. Turn off Auto Generate and click on Generate Lighting to bake your light maps when you're ready, but you're not quite ready yet. First, you need to set all your objects and lights in the scene to static. Then, set your main light, the strongest directional light usually, to mixed mode. Set all of your other lights that are not so important, set those to baked. Now try baking. The rest is mostly just practice. Have fun baking. It is the key to a quality project.